All right, we're going to look at each of these integrals, determine if they converge or diverge, and if it converges, evaluate it. Okay, the integral from 1 to infinity of 1 over x to the 1.1 dx. And there's some little algebra hints here that we'll use. So instead of going to infinity, we're going to go to b, the integral from 1 to b of 1 over x to the 1.1, which I'm going to rewrite as x to the negative 1.1, because then it's easier to use the power rule. And then I have to take the limit as b goes to infinity. So until I actually take that limit, I have to write this down at every step. The limit as b goes to infinity. And now I'm going to take the antiderivative of x to the negative 1.1. So I add 1 to the exponent, and I get x to the negative 0.1. Divide by the new exponent, negative 0.1. I'm going to evaluate that from 1 to b. So just copying down the limit as b goes to infinity. I'm going to rewrite this expression right here, moving the negative exponent to the denominator and rewriting the 0.1 as the root, the 10th root. So this is the 10th root of x in the denominator. And then dividing by 0.1 is the same thing as multiplying by 10. So I've got negative 10 in the numerator. And I evaluate that from 1 to b. Okay, so let's see, I'll move to the next line here. Now I'm going to plug in the b and plug in the 1. So I'm still carrying this limit along. I don't stop writing that until I actually take the limit as b goes to infinity. So if I plug in the b, I get negative 10 over the 10th root of b. And then plug in the 1, and I get negative 10 over the 10th root of 1. Okay, so now I'm going to take the limit. Think about what happens to this fraction as b gets really, really large. So as b gets really, really large, so does the 10th root of b. So the denominator is going to infinity, which means this entire fraction is going to 0. So this ends up being 0 minus negative 10, which is 10. So this came out to a finite number, which means the integral converges. Number 2. Similar setup. I'm going to go from 1 to b instead of from 1 to infinity and take the limit as b goes to infinity. I'm going to rewrite 1 over x to the 0.9 as x to the negative 0.9 dx. And now I'm going to take the antiderivative. So I'm just copying down the limit as b goes to infinity, the antiderivative of x to the negative 0.9. So I'm going to add 1 to the exponent, and I get x to the 0.1 divided by the new exponent, evaluated from 1 to b. So that is the limit as b goes to infinity. And I'm going to plug in b and 1. So when I plug in b, I get b to the 0.1 over 0.1, which is 10 times the 10th root of b. And when I plug in 1, I get 1 over 0.1, which is 10. So if I take the limit as b goes to infinity, the 10th root of b also goes to infinity. So this goes to infinity, and I have infinity minus 10, which is still infinity, so this diverges. The integral from 1 to infinity of 1 over x dx. So I'm going to integrate from 1 to b and take the limit as b approaches infinity of 1 over x dx. This one is a little bit different because the antiderivative of 1 over x is ln x. You don't use the power rule on this one. So I'm just carrying along this limit. When I take the antiderivative of 1 over x, I get ln x, and I evaluate that from 1 to b. So this is the limit as b goes to infinity. When I plug in b, I get ln b. Then I plug in the 1. So as b goes to infinity, so does ln b. And the ln of 1 is 0. So this looks like this is going to be infinity minus 0, which is infinity. So this also diverges. And then in general, we can try to draw a conclusion based on these three examples. It looks like we converged when the exponent was bigger than 1, and diverged when it was smaller than 1, and also equal to 1. So it looks like we get divergence when p is less than or equal to 1, and converged for p bigger than 1. Okay, these look similar, but instead of going from 1 to infinity, now we're going from 0 to 1. So the problem happens at 0. I can't plug 0 into this denominator, so I'll have an asymptote there. So instead of integrating from 0 to 1, I'm going to integrate from b to 1 and take the limit as b approaches 0 this time. So this is the limit as b approaches 0. The antiderivative of x to the negative 1.1, add 1 to the exponent, and I get x to the negative 0.1 divided by negative 0.1. Evaluate that from 0 to 1. Sorry, from b to 1. This is the limit as b goes to 0 of, all right, when I plug in a 1, I get anything to the, a 1 to the anything is 1, and then I'm dividing by negative 0.1, so I get negative 10 when I plug in the 1. And when I plug in the b, I get negative 10 over the 10th root of b. So I have negative 10 minus, and then when b goes to 0, this fraction, when b goes to 0, so does the 10th root of b. So the denominator is going to 0, which means that this whole thing is going to negative infinity because of this negative sign. So this is negative 10 minus negative infinity, which is infinity. This diverges. Number 6, similar problem. I can't start at 0 because there's a vertical asymptote there in 1 over x to the 0.9. So instead, I'm going to go from b to 1 and take the limit as b approaches 0, x to the negative 0.9 dx. Limit as b goes to 0. Antiderivative is x to the 0.1 over 0.1, evaluated from b to 1. That's the limit as b goes to 0. Now I'm going to plug in the 1 and I get 10. Plug in the b and I get 10 over the 10th root of b. So the fraction that has a b in it, as b goes to 0, so does the 10th root of b. So my denominator is going to 0, which means this entire fraction is going to infinity, which means this is 10 minus infinity, which is negative infinity. This diverges. I think that's wrong. Okay, yeah, that was wrong. I messed up when I was plugging in the b. Okay, so when you plug in the 1, that was right. 1 to the 0.1 is 1, divided by 0.1 is 10. And now when I plug in a b, I get b to the 0.1 divided by 0.1. So this is 10 times the 10th root of b. And then as b goes to 0, this whole term goes to 0. So this becomes 10. So this converges. Okay, so the integral from 0 to 1 of 1 over x dx, again, I have to go from b to 1 and take the limit as b approaches 0. But what's different here is that the antiderivative of 1 over x is ln x, and so I'm going to evaluate that from b to 1. When I plug in a 1, I get the ln of 1, plug in b, and as b goes to 0, let's see, the ln of 1 is 0. And then the ln of b, as b goes to 0, goes to negative infinity. So I've got the limit as b goes to 0 of negative ln b, which is negative infinity, which is infinity. So this diverges. So in general, our conclusion about integrals from 0 to 1 of x over p. So when p is 1, it diverged. When p was less than 1, it converged. And when p was greater than 1, it diverged. So it looks like greater than or equal to 1, we get divergence. And p less than 1, convergence. Number 9, the integral from 0 to infinity of 1 over x squared plus 4 dx. So first hint is to use a trig substitution to get the antiderivative. And the second hint is to use a graph to determine some values. So this graph that was given, that's not the graph of what we're trying to integrate. So I added this graph of what I'm trying to find, the integral from 0 to infinity of 1 over x squared plus 4. So this is the graph of 1 over x squared plus 4 right here. So I want the integral from 0 to infinity, the area under this curve. So the only problem here is the infinity. So I have to go from 0 to b, integrate from 0 to b of 1 over x squared plus 4 dx, and take the limit as b goes to infinity. So I need the antiderivative of 1 over x squared plus 4. So that I'm going to do on a separate page using a trig sub. So the antiderivative of 1 over x squared plus 4 dx, I'm going to let x be 2 tan theta, which means that dx is 2 secant squared theta d theta. So I come back to my integral, and this becomes 1 over 4 tangent squared theta plus 4. And then dx is 2 secant squared theta d theta. Factor out a 4 from the denominator, so I've got the integral of 1 over 4 times tangent squared theta plus 1 times 2 secant squared theta d theta. And then tangent squared plus 1 is a trig identity. It is equal to secant squared theta. So my secant squared theta cancels with my tangent squared plus 1. Because tangent squared plus 1 equals secant squared. So all I'm left with is the integral of 2 over 4, or 1 over 2, d theta. So now when I integrate, I get 1/2 theta plus c. And then I just have to replace the theta by going back to my original trig sub and solving for theta. So tan theta is x over 2, which means that theta is the arctan of x over 2. So this is just 1/2 arctan x over 2 plus c. So now I have the antiderivative, 1/2 the arctan of x over 2. I go back to my improper integral and copy down the limit as b goes to infinity. Now the antiderivative of 1 over x squared plus 4 is 1/2 the arctan of x over 2, and I have to evaluate that from 0 to b. So when I plug in a b, I get 1/2 the arctan of b over 2 minus, then I'm going to plug in the 0, 1/2 the arctan of 0. So now I'm going to take the limit as b goes to infinity. So the arctan of b over 2, the arctan of infinity over 2, or the arctan of infinity, that is weird, but that's why I gave you this graph. So where does the arctangent, where does the tangent approach infinity? Right? Here at pi over 2. So that's going to be 1/2 pi over 2 minus, okay, so the arctan b over 2 as b goes to infinity, that goes to pi over 2. And then the arctan of 0 is 0. So this is 1/2 times 0. So that comes out to pi over 4. Okay, last problem. The integral from -1 to 1 of 1 over x squared dx. So I'm going to split this up. There's an asymptote at 0. It's important to know what this looks like before we start. We're trying to find the area from -1 to 1, and the graph of 1 over x squared looks like this. It's symmetric over the y-axis. So if I'm trying to find the area from -1 to 1, I could just go from 0 to 1 and double it. Okay, instead of going from -1 to 0 and then 0 to 1 and adding them together, I'm just going to do one of them and double it. So I'm going to say the integral from -1 to 1 of 1 over x squared dx. That's the same thing as twice the integral from 0 to 1 of 1 over x squared dx. And then the problem area is at 0. At x equals 0, I've got this vertical asymptote. So instead of starting at 0, I'm going to start at b. So this is going to be 2 times, I'm going to integrate from b to 1, x to the -2 dx. And I need to take the limit as b approaches 0. So this is 2 times the limit as b goes to 0. I'm going to take the antiderivative of x to the -2, and you get x to the -1 over -1, or -1 over x, evaluated from b to 1. This is 2 times the limit as b goes to 0. So if I plug in a 1, I get -1 over 1, which is -1. And when I plug in a b, I get -1 over b. I'm going to just change those two negatives to positives. Minus a negative is the same as adding. So this becomes 2 times, if I take the limit as b goes to 0, 1 over a very, very small number, because b is going to 0. So this denominator is getting very small, which means this entire fraction is going to infinity. So this is 2 times -1 plus infinity, which is 2 times infinity, which is infinity. So this diverges.